for the
Let's just say it's a good thing that wasn't on video. Let's just say. Told and owned on that. Okay. So 4.6. No, I did not. 4.6. Do you remember section 4.4 where we showed that like two figures were congruent by taking the object and moving it, translating it, rotating it, reflecting it, so that it was exactly in the exact same spot as another figure? Remember we did that? You had to go through a series of transformations to do that. That's what today is going to be about, but for similarity. So it's just like 4.4, but with a dilation element, okay? Because now we're talking about similarity, not necessarily congruence. So let's just talk about these two questions here before we get started. We've learned 4 transformations: translations, reflections, rotations, and dilations. Which of those are rigid? Which of those yield congruent figures after the, we're going to function. And
all of the above except dilations.
All the above except dilations, right? Dilations are not rigid. The other 3 are. Okay? So when we talk about which transformations yield congruent figures, the first 3, translations, reflections, and rotations. Which transformations yield similar figures? That would be the dilation. Okay? So since we're talking about, this section is called, here, I'll show you. Probably can't read it. This section is called Similarity and Transformations. It's like 4.4, but now we have dilations, so we can start with just similarity. Okay? Everything in 4.4 we're showing this shape is congruent to this shape. And we would go through rigid motions like translations, reflections, rotations, or some mixture of those 3 to go from one to the other. But now that we have dilations, we can show that shapes are similar to one another by doing a similar argument, but then having to include a dilation in there. Okay? Because if we dilate, we keep similarity. As long as k isn't 1 or -1, we don't have congruence. So if we're doing a similarity transformation, you're probably going to have a dilation in there somewhere. Does that make sense? You can't just have reflections, rotations, and translations, because that would be a congruence transformation. Okay? Make sense? So this should be pretty quick today. It's just like 4.4, but now we're going to have a dilation in there somewhere, is the idea. Objectives, we're going to perform similarity transformations. We can describe them, right? If they kind of say, do this, then do this, we can do that. Or we can say, oh, if I had to go from this to this, I could do step 1, step 2, step 3. Okay. And then we will do a proof at the end. The book does these, that's not what I meant to do. The book does these proofs in a very, very long-winded way. That is not how I'm going to do these. Okay, so don't think about a formal 2-column proof. All we're going to do here is if we can go through and say transformation 1, transformation 2, transformation 3, then I will be happy. Okay. So it says prove that figures are similar, but it's not necessarily the same type of arguments that we did with 2-column proofs. All right. And the problem that we do today, if you wanted to look at the book, they prove it, and it takes like 3 paragraphs. We're going to do it in like 3 lines. Okay. As long as you understand the transformations required to go from one to another, I will be happy. That's the important thing. Okay. And we actually do see these types of questions on the released questions from the state of Ohio on the geometry test. Okay. When we do question number 3, Mr. Westphal will say, oh yeah, it's the circle one to show that all circles are similar. Remember, they had to move it and then translate it and dilate it and whatnot. So these proofs are on these state tests, okay? But we're going to answer them like they're going to want it to be answered, not like the book's going to want it to be answered. You'll see when we get there. All right, so here we go. Don't write this down, okay? But we learned yesterday that dilations, as long as k isn't 1 or -1, the new figure is not congruent to the original, right? If k is bigger than 1, then it gets bigger than the original. If the k is between 0 and 1, then it gets smaller than the original. So we don't call dilations a rigid motion, right? but it is a similarity transformation. It does keep similarity intact. The shapes are still the same, it's just their sizes are probably going to be different. Okay? And everything, again, the name of this section is similarity and transformations. So what we're going to do is we're going to go through and do a similarity transformation to go from one object to another. And every time we do this, there's going to have to be a dilation involved somewhere. Okay? Could be first, could be last, we don't really know. But there'll have to be a dilation in there somewhere, because if we don't include a dilation, it would be a congruence transformation, not a similarity transformation. Make sense? Make sense? Just like 4, same ideas, but now we're including dilations as well. All right, so let's give this a whirl. So here is a similarity transformation. Give us A, B, and C. Go ahead and plot them to stall for time. A is at -4, 1. 1, 2, 3, 4, 1. And B is -2, 2. And C is -2, 1. I made the little guy. Duke, Duke, Duke. Okay. We've got A, B, and C. Little right triangle. Okay. Now, they say graph the triangle and its image after the similarity transformation. Look at the two transformations they're giving us. Do you agree that this would be a similarity transformation? Right. It would be a similarity transformation, right? Because the second one is a dilation. Okay, so if we didn't have the dilation, if we just did the first one, after that translation, the new shape would be actually congruent to the original. All right. But the dilation with a scale factor of 2 is going to change the size of the object. So we have to call this a similarity transformation, not a congruence transformation. Okay. Does that make sense? Noah, help me out, buddy. Translation. XY goes to X plus 5, Y plus 1. What does that mean? So you can't forget the old stuff. Go ahead. Right, 5 and up 1. Right? So you'll see this stuff on the quiz. So the quiz on Thursday, even though it's only over sections 4, 5, and 6, it's very cumulative in nature. You have to know the translations, you have to know the rotations, reflections, and that kind of stuff. Because they will show up in these similarity transformations. So it's a good cumulative chapter, I would say. So everything has to move right 5 and up 1. Okay. So I'm going to go from B, 1, 2, 3, 4, 5, up 1. I'm going to call that B prime. 1, 2, 3, 4, 5, and up 1. There's C prime. And 1, 2, 3, 4, 5, and up 1. There is A prime. Blue triangle congruent to black triangle? Yeah. Just in different spot. Okay. And then the dilation, xy goes to 2x, 2y. What would we call that? What kind of dilation is that? Yeah, Brayden.
I had it in my answer.
Okay.
What, say times 2 dilation?
Yeah, scale factor of 2 centered at the origin. Centered at the origin. xy goes to 2x, 2y means that it's centered at the origin. So all we're going to do is multiply the x and the y by 2. All right. So let's see here. Schrembeck, 1, 2 will go to 1, 2 will go to 2, 4. Right. 2, 4. 1, 2, 3, 4. Call that a double prime. And Dempsey, B prime is 1, 2, 3, 1, 2, 3, 3, 3. So B double prime will be?
No, 6.
6, 6, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's B double prime. And then Kaler, 1, 2, 3, 2. C prime is 3, 2. So C double prime will be? 6, 4. 1, 2, 3, 4. Duke, Duke, Duke. Do you agree that the green triangle is not congruent to the black triangle? Okay, the dilation made sure of that. We multiplied each of the components by 2, all right, thus lengthening everything by 2. And notice, again, the rays through A to A prime, through B prime to B double prime, through C prime to C double prime, but now they're just twice the distance away. Remember we did those drawings in homework yesterday with, K is 2, just multiplying those lengths by 2. So there we go. Though you don't need to have those arrays drawn in, I just kind of was showing you as a reminder about how dilations work. But that would be the similarity transformation. That's it. Okay. The original is no longer congruent to the newest figure, but it is similar to it. Easy? Easy? Questions or concerns? Let's do example 2. Now we're working backwards. Okay. Now describe the similarity transformation to go from PQRS to WXYZ. From PQRS to WXYZ. What do you think here? Kayla, what do you think, buddy?
Can we do a reflection and then a dilation?
Okay, it looks like it's probably going to be a reflection and dilation. I agree. Does it matter what order?
Yes. No. I don't know.
I don't think it does. In this case, it might sometimes. In this case, I'm not sure. Again, I'm not great at visualizing this just on the fly. It's not my strength. If I'm going from blue to green, what kind of dilation am I going to have to do? Is it going to be an enlargement or a reduction? It's going to be a reduction. So K has to be what? Bigger than 1 or smaller than 1?
No.
Smaller than 1. Okay. So what do you want to do first? Do you want to dilate it and then reflect it? Do you want to get it like the same? Do we see what K is going to be in this case? Yeah. 1/3, right? Do you agree it's going to be 1/3? Because notice here, this length is 2. Oh boy, that's not what I meant to do. Sorry. This length is 2. What's this length? 6. What's 6 divided by 3? 2. Okay. This length is 2. This length is 6. This length is 1. This length is 3. It's a 3-to-1 ratio. And you're going from big to small, so you better do a dilation with a scale factor between 0 and 1, and which in this case would be 1/3. All right. If you were going from green to blue, then you would dilate by a factor of 3. Okay. So let's do that first. Let's do the dilation first and then see what happens. And then we'll decide whether we can just reflect or if anything else will need to happen. So let's dilate centered at origin with K equal to 1/3. Okay. So let's see. 0, -3 will go to 0, 1. That's R prime. -6, -3 will go to -2, -1. It's S prime. -3, 3 will go to -1, 1. It's Q prime. And -6, 3 will go to -2, 1. That is P prime. Book, 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 book. So the dilation does a pretty good job. And then what do we have to finish off with? Someone else. Swinehart.
Reflect.
Over the
Why?
over the y-axis. So step number 2, reflect over the y-axis. Okay. Now, let me draw your eyes to statement number 1. It says dilate at the origin with K equals 1/3. You really should specify here that you're going to dilate centered at the origin. Okay, you should really, really specify this. Because the next problem that we're going to do, the little proof, problem 3 is actually the last problem that we're going to do today. We're going to dilate not necessarily at the origin. You're not always going to have a coordinate plane here. All right, here we do have a coordinate plane. And so it is smart to specify the point, okay? I would expect to see you saying dilating it centered at the origin with a K being 1/3. Okay, specify the point, the center point of that dilation. Okay, in this case, center it at the origin and then we would do a reflection over the y-axis, and then we are good to go. I think we could do those in any order. Do you agree that if I reflected first, then dilated, I should get the same thing? I think. I don't know if that's always true in general, but in this case, you would definitely get the same thing. Mr. Westfall, you're good at visualizing these things.
What's up?
If you dilate and then reflect, is that always going to be the same as a reflection and then the dilation? Does the order matter? He's more like a three-dimensional guy. Think about it.
About the original ones?
Yeah. Seems to me maybe. I can't think of it. Think about it.
I would think so.
My first instinct might be right. Questions on number 2. All right, now, you will also have one homework question like this. Okay? And it says, proving that squares are similar. And they have 2 squares oriented for us. We've got square ABCD has side lengths of R. Square EFGH has side lengths of S. And it tells us these lines are parallel. I think it's a little bit overkill in my opinion, but whatever. It tells us lines are parallel. And then we're trying to prove that this square is similar to this square. Okay. This procedure is virtually identical to when you had to show that 2 figures were congruent. You had to go through those rigid motions and make sure that one wasn't exactly on top of the other. Same thing here, but with similarity, you're going to have to incorporate a dilation. Okay, you have to incorporate a dilation somewhere. And so generally speaking, what you want to do first is you want to get one point matching up with the other. All right. So notice here the square is on the left. Maybe it's a little bit below. Doesn't really matter. Instead of writing a long-winded paragraph proof, if you open up the book, it's somewhere around page 200 or something like that. The book goes through a long 2-paragraph, 3-paragraph argument as to why this works. I think it's a little bit beyond what high school geometry needs to argue. Let's argue the transformations. What transformations do I need to go from one to the other? And be as specific as possible. Okay. My recommendation to you first is translate ABCD so that A prime is now point E. So what I'm saying is I want you to pick up this object, okay, and I want you to move it so that it looks like this. Duke, 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 Duke. And this is A prime right here. Does that make sense? A prime is E. You translate it so that that left-hand corner of the little square is touching the left-hand corner, lower left-hand corner of the big square. Okay, does that make sense? Now, let me ask you this. What would have to come next to make the red square exactly the same size as the big square? What would have to come next? It'd have to be a dilation. Now, I want you to be here's the hard part, okay? I want you to be as specific as possible. If we're going to have a dilation, you need to give me 2 pieces of information, okay? First of all, then we're going to dilate. I want you to give me the center point of that dilation, and I want you to give me the scale factor of that dilation. I will grade you on that. I want to see the scale factor, and I want to see the center point, okay? If this red square wants to look just like the big square, what needs to be the center of that dilation? Beta, rethink. Exactly. Do you agree that A prime or E, either one, that point needs to be the center of the dilation, right? Because the center of the dilation doesn't move, right? And we moved A to, we moved A to be on top of E. A prime is on top of E, okay? But if we're going to dilate this, the center point needs to be this point that we want to keep still, right? The center point of a dilation never moves. Are we in agreement with this? You see that the center point needs to be A prime or E. Say either one, doesn't matter. Okay. Dilate centered at E, let's call it that, with K. Okay, now, what does the scale factor have to be? Look at the length of the big square. Look at the length of the small square. What does my scale factor need to be? Right now, this small square only has a length of R, but I want it to have a length of S. What does that scale factor do to the lengths? What does K need to be to take this square with side length R to make it a square with side length of S? Tough question. Right.
Like, it's not going to be smaller than 1, but it's not going to be more than 2. So it's like 1.
Okay, that's true. Okay, so you're looking at it as a scale thing, right? I'm telling you now that you can be more specific than that. You can give me an action. Now, it's going to have letters, not numbers. It's going to be a general argument, not a specific argument. Close. If I do a scale factor of S, what's going to be this new side length? It was R, scale factor at S, so what's going to be the new side length? No. Say original shape has a side length of 2, and then you do a scale factor of 3. What's the new side length? You multiply by 3. 6, right? If we did what you just suggested, this length would now be R times S, not S. Okay? The question is, what do we need to multiply R by to end up with a length of S? It's a tricky little thing. What do I need to multiply R by to get a length of S? Bader. What's R times R? R squared. R squared.
Bro, this is so weird.
What do I need to multiply? Schrebeck? No? What do I need to multiply R by? Let's call it X for now. What do I need to multiply R by to get S? Nope. Nope. Let's solve for this X. What do I need? This is going to be my scale factor. Okay? What do I need to multiply R by to get S? Let's solve for K. Let's divide both sides by R. Really?
It doesn't make any sense.
What is R times S divided by R? What is R times S divided by R? What is R times S divided by R?
No.
What is 5 times 2/5? 2, right? The 5's cancel. What's R times S divided by R? Just S, right? Don't these R's cancel? S divided by R is my scale factor. Let me do it one more time.
That doesn't make sense.
It makes a lot of sense. It makes perfect sense to me.
Down to me.
Well, let's try it one more time. Do you agree? In general, say you have a square side length 2. Say you dilate it by a scale factor of 5. What's going to be the new side length of that square?
Fifths.
No.
5 feet. Seconds.
That's not a number. It was 2. You dilated by a factor of 5. What's the new length? 10.
Oh.
Let's change the question. Side lengths are 4. Then you dilate it by a factor of 5. What's the side length going to be? 20, right? We take the original length, we multiply it by the scale factor, and we get the new length. Yes? Old length times scale factor gives me new length, right? Right? Now, what's my old length? R. Right? It's the side length of the red square. What's my scale factor? Well, that's my unknown. That's what I'm going to try to figure out. What do I want the product to be? What's the new length? S. So do you agree that whatever R is times my scale factor better give me S? Do you agree with that? R times my scale factor. Old length times scale factor gives me new length. Old times scale gives me new. Okay? Well, how do I solve for the scale factor? Divide by R. Don't these R's cancel? So scale factor must be S divided by R. Prove it. What's my old length times the scale factor? What happens to the R's?
Cancel out.
Cancel. Won't this length now be S?
Yes.
There you go. Okay. So K has to be S divided by R. You gave me two pieces of information of dilation. You told me the center point, which in this case was A prime or E, either one would work. And you had to tell me the scale factor. In this case, the scale factor has to be S divided by R. Okay. If you said R divided by S, I know what you're doing, but the R's don't cancel. It's R times S over R. R's cancel, you're left with an S. Okay. Does that make sense? If you get a question like this, I think it's problem number 11. Just give me the steps. Give me the transformations. Kyle.
So if we have a question like this on the test, do we have to do like all that work and just put what we're trying to get to over the original? And that's like
Well, if you can do this in your head and you say K equals S over R, that's okay. I'm trying to show you, if people don't believe me that S over R is the scale factor, I'm trying to convince them that S over R is in fact the right number.
but is that right? Like if you just put what you're trying to get to over the original, is that like the answer?
Yeah. Isn't the scale factor new divided by old?
Yeah.
New divided by old. What's the new length? S. What's the old length? R. Right? So it makes sense. New divided by old. Okay. Questions? If you want it to be 10 and you have something that's 5, what has to be your scale factor? You're at 2. Right? That's it. New over old. New over old. That's it. Okay. Questions? All right. That's all I got for you. Tomorrow,
Can you go back?
I'll give you problems to work on. It's only 1 through 11, so it's only like 5 or 6 problems.
Can you go back? I was writing that down.
This?
Yeah.
So tomorrow, I'll come in with the problem set. Did you guys like working together and then having a video to go to if you needed it?
Yeah.
Okay, let's do that again tomorrow if you think that was helpful. So I will come in. I'll get a video made at some point in the next 34 hours ish.
Well, what company are you not going to be in?
What? What?
I'm confused. I don't know what you just said.
In the next 34 hours, I will make a video with the solutions to the problems I'm going to give you tomorrow.
Oh.
I'm going to give you a problem set tomorrow to work on in class when I'll have a video posted. As long as the videos are processing the Screencastify. And there's your homework. Page 211, numbers 1 through 11 on.
Yeah, we got plenty of time to do all this.
You have 10 minutes right now. Go ahead and get to work.
Unless it's